Hello everyone, welcome to today's class. So last time we covered some ideas about layer descent, and in particular we looked at a particular view of layer descent where you use a function h between the original space, the space where your iterates lie, and the space where your gradients lie. Right. So you in particular use for function h you use a map gradient h to map from the original space to the gradient space, and you use the inverse of the map, or or maybe you use the gradient of the differential dual to go back. And then inside this other space, you do a step. Here you do what you should do. You just step of minus learning rate times the gradient. So here you do the step, and and this is basically the algorithm. And we showed some applications of this. So the key application we showed is what if you have a different norm? So if your gradients are bounded, specifically if you're working with a norm where let's say h is strongly convex in some norm, and your gradients are bounded in the dual norm. Because it's something it's at most maybe some row. Then you get a nice guarantee. So you get your usual row over root T kind of convergence. Essentially, this was the idea. And today we will do a different view of layer descent. So different view, or maybe or implementation of the same idea. And you can see how that's all useful. So layer descent has seen like many paths of evolution and many interpretations and implementations. So we'll see different method. And specifically, we will use this to recover one of our old results, recover nested rows acceleration. So that's a plan. So hopefully this will also provide a better understanding of acceleration and gradient descent generally. Okay, so first let's just see what this other view is. So this is called the proximal point view. Okay, so what does this say? So the idea is that your gradient descent can be thought of as your xk plus 1 is the minimizer of some quadratic. And how do you obtain this quadratic? So when you take the linear approximation, so you say the linear approximation is some gradient or subgradient at xk and x minus xk. Okay. So let me just write the full thing. So the linear approximation of the function at xk is f of xk plus this quantity. Yeah, so this is what you would ideally want to do. The problem is that this linear approximation is of course not accurate. So this argument can take you very far from your from where you want to go. And this f of sk is just constant, so I will just ignore this. And I will, well, this argument over x. And I will add what's called a regularizer. So I will try to prevent my x from going too far away from xk. So we'll add some penalty or regularizer. And what is penalty? This penalty is simply maybe the L2 distance squared. Yeah, and maybe I can put some learning rate somewhere. So I don't have to weight these two terms equally. I can weigh them differently. So maybe I put some alpha somewhere. Maybe I put an alpha. Okay. So that's what I want to do. So, and let's see how you will do that. So let's just differentiate this. So you get that alpha gradient of xk plus x minus xk would be 0. Right? So yeah, so this is saying that so this is gradient descent with alpha equal to eta, right? Yeah, sorry, in front of just writing eta here. Why am I getting alpha? Yeah, so yeah, and that goes gradient descent. But now one might ask that, okay, is it a good reason why this penalty is the right one? Especially if maybe you're working in a different norm, then maybe the norm will also be different. So yeah, so here comes the new idea that instead of this penalty, you use a different penalty. So use a penalty which is the Bregman divergence. Okay, so let's see what happens now. So so now what's the algorithm? So xk plus 1 is argument x plus the Bregman divergence between okay. So yeah, so the algorithm, let's just recall what this is. So what is Bregman divergence? That is just, so remember I have a function h here, right? So function h here. So this is h of x minus h of x here. So we have this. Great. And now suppose I do the same thing. So now again differentiate. So now let's see what happens. So now I get again eta times gradient of f at x as 0 plus gradient of h at x minus gradient of sorry. It's just gradient of h at x. Yeah. And I want to make it 0. So then what do I get? I get that x should be so gradient of now I just change sides. I get gradient of h at x should be gradient of h at xk minus eta gradient of f x. And it is exactly the mid-descent iteration. Yeah, that's what xk. So this is like xk plus 1. That's next. Yeah. So yeah, this is precisely what we did last time. Okay, yeah. So there's the other view of mid descent. And yeah, I guess both of these views are kind of equivalent essentially. And now let's see some applications of thinking in this way. So the one good thing is that this view it brings the Bregman divergence more directly inside this. So it kind of tells you exactly what x is. So only you have to think in 2 steps that I'm going to the gradient space, then I'm going back, and then which is more complicated to think. But now it's kind of more direct. That look, I don't have to go to any other space. I can stay where I am. I just have to move according to this other penalty function. And this simplifies the analysis also, and it gives like other interpretation. So let's see. So the first that is reconstruct the analysis of mid descent using this interpretation. So I will just prove the essentially the main lemma which we proved last time. So remember we used the Bregman divergence as a potential to prove things. So I will just prove that lemma. That's all that matters really. So we prove this main lemma. Prove main lemma of descent once again. So I want to show that if xk plus 1 is so for this iteration, I want to show that eta of xk minus any f of u. So you had will typically read the previous xk, right? But I just write u here. So this thing here should be so we show this actually. This is at most eta the end of xk. Sorry. Yeah. Okay. So this doesn't require anything. This is just convexity. And but we show that this quantity here is at most eta squared by 2 gradient of xk dual ln square plus the potential decrease. Okay. Yeah. So you have any point. So think of U as the optimal point. You think of U as X star. Okay. So there's the mail now, and now we kind of show it in a more clean way using this interpretation. Okay. So let's just work it out. So let's just figure out what this quantity is. So this quantity. Well, this is okay. So now break it into two steps because I want to compare the two things. So this is theta xk minus xk plus 1 plus xk plus 1 minus u. And now, okay, let's use the first term. Okay, and now the second quantity, I want to bound using my iteration, right? So what do I know about max k plus 1? I know that it's a minimizer of something, right? So I know that xk plus 1 minimizes xk x minus xk plus the fragment divergence is beta, right? Which means that if I plug something else here, it should only be bigger. So therefore, yeah, actually, even better way. Okay, so if I just find a gradient, that's even easier. So okay, so I just write this down. Okay, okay, so what's the gradient of this quantity? Okay, let's try the gradient actually. So gradient was theta gradient f plus gradient of h, right? Or heading too fast. So this should be, yeah, gradient of h with x minus. Okay, so that's the gradient at xk plus 1, right? And okay, actually, if I now so today I want to do it for generality, so I want to also assume that there's a constraint set. So this constraint set, let's call it Q. Then suppose this is my point. Xk plus 1, which is a minimizer. So and here is my u. So it's u somewhere, right? So what do I know about this vector and the gradient of this function? So remember, I'm minimizing this function.
U is convex and
So, and that has to be a Q. Yeah. So I'm minimally over a convex set.
Yeah. Then the gradient in direction of you will be constant.
Yeah, exactly. So this inner product with u minus xk has to be non-negative. Yeah, so that's what it gives me. And now I can plug this back here. So this gives me that. So this is at most. Yeah, this is at most gradient of xk plus 1. Maybe we should write almost it. I'm going to first. Okay, so I think there's xk plus 1 here. Okay, there's a plus 1 here. Yeah, okay, the plus 1 here. Yeah. So this. Okay. Yeah, and a product, yeah. Yeah, exactly. So that's what this is. So I'm getting an extra gradient term here. I think it's fine. Yeah. Yeah. And in fact, now one can say, okay, so I think this is equal to say that, oh, okay, I just rewrite this so it looks nicer. So I claim that this is equivalent to saying that the gradient of f, the gradient of h, I mean, of the fragment divergence actually. So yeah, fragment divergence between xk plus 1 and xk. I think this would be right. So I think I just write it this way. Yes, I just use this form instead of the previous one. It's the same thing, right? Yeah. So yeah, so basically I get the same thing, but I instead get I think I'll just erase this. Exactly the same thing. And yeah, so here I just get minus gradient divergence. Okay, yeah, so this will be easier to manipulate. We'll see why. So I think there's no minus signs. Plus. Yeah, okay, yeah. Cool. Okay, so now, what do we know about the payment divergence, right? So we have seen this triangle inequality, or yeah, so let's try to use that now. So we had, okay, so let's copy the thing from the previous slide. So yeah, I just reverse the sign. It's the same thing. Yeah. And now I used the triangle inequality to say that this quantity is at most the Bregman divergence. So this is DH. DH xk plus 1 xk. Yeah, and now I know by triangle inequality that this quantity is in fact at most d u xk minus d u xk plus 1 d. So I think I've switched it once again. U U. Okay, yeah. Yeah, so that's the thing we saw in the first class on Bregman divergence. So yeah, so that's the Pythagorean inequality for Bregman divergence. Yeah, so I guess all they're saying is that if I have these 3 points, xk plus 1 and u. Then the Bregman divergence between xk and u versus if you had gone from u to xk and then from xk plus 1, from u to xk plus 1 and then from xk plus 1 to xk. So how much would your difference be? And that's this quantity here. Okay, anyway, so that's the yeah. The theorem which we I think already did in the previous class. Anyway, so and now let's continue this. So this is at most this, and yeah, I guess now a few more steps. So this is yeah. So now I have to use the fact that Bregman divergence is also Pauli convex. So let's do that. So for that I will be able to eliminate this term. But this is thing which I need for my this is my finite inequality, right? We have these two terms which I will cancel in the final argument, but okay. So I will keep these and I get minus, yeah, and by strong convexity I get that this is xk plus 1 square by 2. Yeah, so for now this is given that it's one strongly convex. So if it's some other alpha, you can just put alpha here. Yeah, so the primary device is at least this. It's a minus sign, so I get at most plus what I wanted. And now finally, yeah, and now I'm almost there. And now using Cauchy-Schwarz and by completing the square, this is at most what I wanted at most square. Yeah. Yeah, so that's the proof, and I think you have to see how this most like the last time. So the last time there were probably a lot more terms and many steps, but by just observing that this is the minimizer of this, and you adding things and using this Batra inequality, you're able to get it much more clearly. So anyway, so I guess I want to do this proof for completeness. Okay, and now let's see how to use this to do our good stuff. So okay, so what's the goal for today? Okay, ambitious goal. So goal is to kind of derive Nesterov acceleration using mere descent plus gradient descent ideas. So so let me write what the algorithm would be. So so the idea is that both mere descent and gradient descent have their own advantages, and the question is that can you just maybe combine them one after the other, and in such a way that you're able to get acceleration. So here's the algorithm which we will use. So what need to combine? If I will combine in the most stupid way, is a linear way. So let's do that. So okay, here's the algorithm. Okay, first of all, okay, what do we know? So we have a function f, which is L smooth with respect to some arbitrary norm. Yeah, so now everything is general norm. And let's say you have a function h, which is one strongly convex with respect to the same norm. And let's say x0 is some initial point, and let's say you know in advance how many iterations there are. So right now I will do it a bit sloppily. So I will assume that you actually know the optimal value. Yeah, that you may not know, but let's say a person guessing trick, you know it. So if you know the value, you don't know the point, but we'll show you how to find it out. Okay, so let's see. So for k equals 1 through t minus 1, so you do the following. So at any point, I will maintain a bunch of variables. So what's the idea? So idea is, let's say my current iterate is some xk. Now I want to do two steps. So first is a gradient descent step, which you know very well. So I want to do some. Firstly, yeah. So I want to say that yk plus 1 is xk minus eta gradient. So, okay. So I want to do this step, and I also want to do a mirror descent step. So zk plus 1 is arg min the Bregman divergence of z with respect to the current point plus my product eta. Okay, so I actually should also write an xk plus 1 first. Okay. So okay, so the way this is labeled is, so we first find an xk plus 1, which is a linear combination of my two previous iterates, which is some gradation iterate and some gradation iterate. So this is some tau times zk, yeah. Yeah, this is called tau k times zk plus 1 minus tau k times yk. Okay. And then okay, let me just call it xk plus 1. Okay. Here you do, sorry, this is z. Okay, cool. Okay, so that, yeah. Okay, so let's understand this. Okay, so at any point here, yeah, so you submit it, and then you do two steps. The gradient step and the mirror step. So the gradient step you do on the previous x iterate, which was the linear combination of the previous z and y iterates. And the mirror step you do the previous z iterate. And notice, however, that here you have an x instead of a z. Okay, so I'm using the gradient from the x, but I'm doing the iterate of the z. Okay, so this is like slightly different from the usual mirror descent. In the usual mirror descent, you have x here and also x here. Yeah, but here is slightly different. I mean, with the gradient from x, but I'm doing mirror descent step on z. Yeah. And what's the idea for this? Okay, so the rough idea is the following. Okay, so yeah, what I would do something of this type. So let's give the intuition. Okay, so the intuition is as follows. So we just look at the gradation analysis. So gradation seems to work well when gradients are small. So when you look at my grades xk and I look at their dual norms. So when these were small, my guarantee is actually better. Right? Whereas if you have a gradient descent, so gradient descent does well when the gradients are large, because when gradients are large, then you make large steps. Gradients are large, then you can make large steps. Okay. Yeah, and then the idea is that somehow by using the same gradient in the two steps, we try to get best of both worlds. So if my gradient is small, then my second step will essentially be the workhorse, and the gradient is large in the first step will be the workhorse.
So Nestor's original thing also looks a little bit like this, right? Because he has this quality approximation thing. Isn't that going to look like that thing said?
Yeah, I think the algorithm kind of looks the same. I mean, ultimately it does look the same.
No, as in like his derivation also is of this kind. Like he says, you see every point you have a local quality approximation and you minimize it.
Right.
Like so you keep moving the center and the radius of the quality approximation.
Yeah.
So just similar or even the derivation. When final updates probably look the same.
Yeah, of course. Yeah, final updates look the same.
But I was wondering even at the level of like so he has a thing that what you do say is you have this function which is like a convex combination of the actual function and a quality approximation. But then what is it? You minimize the quality and then keep moving the quality slowly. But then to update, you have to change. You have to like look very carefully fix the rates of how you are updating. Yeah. So okay, I guess maybe look at analysis first, and then we can kind of see what happens. So the thing is about to come up with this, but doesn't have to go through the entire thing of coming up with these quadratics and finding these. So I remember we had to solve this quadratic equation also. Yeah. So all that didn't flow. Okay. Okay. Yeah. Okay. Anyway, maybe let's first see. Then we can see actually very different or not. Okay. Well, okay. So that's the algorithm. So yeah, just to in nutshell. So you look at the gradient at xk plus 1. You do with the same gradient, you do a gradient step and a mirror step. And yeah, I guess that's the thing. The gradient uses the same in both steps. Okay, so now let's see how to analyze this. Yeah, I think the analysis is like it's much cleaner. Right? I think I thought it is. Okay, maybe I'm wrong. So let's see. So here's a kind of easy lemma, which kind of follows immediately. So eta times gradient of f at k plus 1 zk minus u. So you use any point, think of the optimal point. This is at most eta square by 2 rho log square plus the difference in the potential.
And this follows immediately from the previous analysis of build descent. So yeah, this is exactly the same thing. Yeah, so I haven't done anything. So the only slight trick is that in that analysis, zk was same as xk. But yeah, basically you just put xk equal to zk everywhere. So you get the same. Yeah, so nothing's happened so far. Yeah, and now I plug what I know about gradient descent. So this is now at most eta square L f of xk plus 1 minus f of yk plus 1. Right, because that's how gradient descent works. So this is our old thing which I've seen many times. Okay, so yeah, so you know all of this. Great. Okay, so now ideally what one would like to do is then just add things and telescope, right? Like one usually does. Of course, the problem is that you have an xk here and a yk here. So you cannot cancel these things. So okay, and that's why we have to do this linear combination, and somehow that is enough to handle this issue. So let's do that. So let's see. Yeah. Okay, so I did that too. So one is that here you have this xk and yk, so you can't cancel. And also on the left side, you have a zk here. And what you actually want here is xk. So well, if I had put zk equal to xk, then the left side would be fine. It is what I want. But then on the right side, it doesn't match up on. Whereas if I put yeah, exactly. I think that is the issue. So yeah, on the right side, not match up then. So okay, so well, let us see what the difference is if I use a linear combination. So what the difference between what I want and what I get with a linear combination? So the difference on the left side is what? Is eta times remember what was zk? Zk was a linear combination. It was some let me just write this. Yeah, let me write this first. So the difference is just okay. So essentially this put zk here. So it's just this, right? Yeah, that's the difference. And this is yeah, and now yeah, what was he getting? So you can show that tau times xk plus 1 minus zk is 1 minus tau times yk minus c plus. Okay, yeah, so that's on the definition of xk plus 1. Yeah, yeah, and now I can use this here. So this is exactly one minus tau over tau eta yk. So right. that is at most. And that's psychometric. So okay. So that's the difference between okay. So this is the additive minus the true error. Yeah, the true.
No, it's error minus so right now. LHS is about the bond.
No, okay, edges of the above. Okay, so okay, I should probably written it. It's getting confusing. So this quantity minus. I guess you know what I mean. So okay, so yeah, so the gap is at most this, right? And now I want to like add this gap on the right side. So eta times. I think I'll just write the final thing and then you'll see what I'm trying to say. So this is what I want, right? So this is now at most this thing plus this thing, right? Clearly. Okay. And now I will get what I want if I choose my tau carefully. Yeah, yeah, and that's also kind of obvious, right? How to choose tau. Because all I want is that my f of x k plus 1 should cancel. So what do I need? So I need that eta should be 1 minus tau. Okay, so I'll time eta should be 1 minus tau or tau. So, yeah, so as long as you use tau like this, you're good. So this is at most. Okay, what is this? It's at most L times. Yeah, eta square L. It's right. Eta square L f of yk minus f of yk plus 1 plus the potential difference. Yeah, that's it, right? And now we're done. So now you just add everything and thing on the right cancels. And now then, okay, what do we get? Okay, so I will get that eta. So just add over t steps. T times. Yeah, which is just the average of the average iterate of x bar. Let's see, average iterate minus f of. So let's put x bar now. It's just put t equal to x star. Maybe just write e minus f of u. Use whatever point you care about at the moment. This is at most s square L f of y0 of yt plus the potential difference. Okay. So okay, so you will get this. And okay, so now okay, so what does this mean? It means that if this quantity is at most some number really, and let's say my initial potential is at most some capital theta, then it means that I can get an difference of theta LD over T plus theta over theta T, right? And now I just optimize theta, so theta should be what? Theta over LD square root. And yeah, and then I get that this is the most something like root of LD theta over T. Okay, well, now on the face of it, this looks a bit bad because then you're only getting 1 over T convergence. But the thing is that your learning rate is 1 over root T now. So which means that you can just repeat this process by changing the learning rate. Okay, so I guess here is a small trick. You have to change eta now after every phase. So in each phase, let's say you half your T. Yeah, and then you change it accordingly and then repeat again. So if you do that, then it's okay, that's fine. Okay, so this means that okay, so to get the distance T by 2, we need roughly square root of okay, so this is okay, so this is like okay, so I got T over 2 here, so you need roughly essentially how many steps you need? L theta over B steps, right? Yeah, essentially you need many steps. Okay, yeah. I guess now this suggests what to do. So yeah, then now you just repeating this process by changing the learning rate. And yeah, so if I want to get an epsilon error, then yeah, how much time will I need? Well, it will be roughly L theta over epsilon plus theta over 2 epsilon 4 epsilon. So yeah, and that's what you want. Right. So yeah, and that's the correct rate.
I don't know what's different.
Yeah, so so
it's changing so there in some sense the rate is changing at every step.
right, but where rates changing after every phase. Yeah. So yeah, so superficially,
I think what will happen in that case, if you do anything mess around with this, because quadratic, what will happen is that you so this is recurrence kind of thing, right? That there's 1 over root of the learning rate that change that changing. So that probably will now be like it remains fixed for a while, then it becomes half. Then
yeah.
So I think that will the lambda just keep it fixed for a while. So there it's like a quadratic kind of. So you try to have a quadratic which is a lower envelope of a convex combination of the function and original starting quadratic.
Yeah.
And then you slowly, and this convex combination is that way you move closer to 1 further.
Yeah, right.
And that's the one that moves like 1 over 1 over t square. So 1 over lambda, 1 over square root of lambda increases linearly in the analysis. But now instead of increasing linearly, then it just be doubled after half after everything. So I think the lambda will play the role of t or something.
I see. I see.
That you keep the same mixture, the mixture.
Which remains the same
Keep it fixed for a
for a
while,
while.
and then
Then
the quality equation probably will not show up again.
maybe. Yeah, possibly.
If it works for it, then you will. Because now in the beginning there is no interest that will be better than so you forget about one like I like starting like in Nestle all this. Why should you believe when you're starting the analysis that it will be at least as good as or better than grading? That's not fair. Is that
Okay, so I guess we need to hear what can try to heuristically justify. So it's like the kind of vague justification here can be distracting. It's like everyone is like okay. Okay. So what's the idea, right? So heuristic justification. Okay. So the point is that when the gradient is large, so let's say your gradient is yeah. So let's fix a threshold k. Okay. So fix threshold k on gradient. Okay. So then here is like a sloppy algorithm, which will not work. But just to like justify that something can work. So when gradient is at least k, you do gradient descent. Okay. For t steps. And otherwise do mirror descent for t steps. Okay, so and there's nothing update which I wrote in the previous slide. So mirror descent to do the argument of the segment divergence plus. This great descent is equal. Okay, so this copy algorithm which is not written properly won't work also. But the idea is that this can give you a good rate if it works. So why? Okay, so okay, so
mirror descent to which divergence? Or which whatever what is it called mirror.
Okay, so okay, so the recipe is that you use any edge which is strongly convex with respect to your norm.
But usually you fix one specific one. So for the next to recover the rest of thing you use what
yeah, I guess there you would just use the
norm square.
yeah, exactly, norm square, because everything is Euclidean. Okay. Yeah. But actually, if you do that,
but that is just
then that is the same thing.
If you do something.
No, I mean, in analysis, we haven't used anything else.
I understand.
So the analysis it was just one slide analysis, right? So we didn't do anything. It was literally just one slide.
No, but mirror descent with mirror map fixed to the each square will be not is exactly.
Yeah. So
then the thing is here you're doing meditation, but you're like taking gradient of one point and you're getting a different point, something like that. So
no, but it's still mirror descent will be exactly the same as mirror descent.
Yeah. So the thing is that
the map, the identity basically.
So you can never diverge, so it will just
right. Okay. Good. So it is going gradient descent, and I guess so if you do that. Okay, fine. This is also gradient descent, right? But the thing is, if the gradient descent was decay, this gradient descent unexpected. That's one difference.
what is your starting decay?
So I guess it doesn't really matter here, because ultimately all you need is a bound on the diagonal divergence, or whatever the distance, right?
Oh yeah, so this is the quadratic approximation. So because the TZ will look like a
quadratic.
Yeah, and yeah, okay, so you're doing it. So the gradient descent on the quadratic is so in the next one you just say minimize it because the quadratic is minimize in one like you can complete that
Optimum thing.
So maybe that's the one. So
Okay, so yeah, so well, this is another gradient scale.
let's say so y plus one gradient of. So what is the gradient between y in that case? So y.
No, so
you do the gradient step on x, that's yk.
And you do the gradient step on ck using the xa gradient.
Yes, but where is yk being used?
That's in the next iterative.
Oh, xk is the convex combination of the okay.
Yeah, so you do gradient step. You do
Never you minimize the function, you do gradient over the function and on the quadratic approximation of some kind. So that dzk like you don't need a quadratic approximation of the function, it's a some quadratic.
Some quadratic, yeah.
Just some quadratic. And you do this and then you combine. Whereas what Nesterov would do is try to ensure that each step the quadratic is such that it is the convex combination of functions. Here you're saying, okay, no, I'll just take the data and take on. That's
So what happens if you pick z not equal to x, no? And your relation is declared in one.
So so indeed, I think as you said, diagram is slightly different now. Because this is no longer a valid lower envelope. Because you're taking gradient at some point. And but okay, because here you have given dk square, but here you have gradient at xt.
so even next thing you don't have valid lower envelope. It's like it's a lower envelope of some convex combination of functions and another quadratic.
Yeah, but
that is important.
That's important. And then as iterations go, the other thing it drops in its weight.
The other thing drops in its weight. That's so.
But here, where is that dropping happening?
Tau is going to be
The tau is used.
The tau is controlling that. And I guess the tau related to learning rate, right? I think that's what will happen. Yeah, because
what is the tau?
Oh yeah, let's check that.
So your eta is 1 minus.
Yeah, that's the thing, right? Eta is eta is 1 minus tau or tau. So as iterations go, your eta will decrease.
Tau will increase.
And tau will increase. Which means that
that's very strange.
Or is eta decreasing or increasing?
So 1 minus tau or tau will increase. Will decrease. So that means your tau will increase.
No, okay. So as iterations go, d will decrease. So tau, so eta is
increasing. Okay.
Then
So
increasing.
1 minus tau will.
That's going to be the right.
Yeah.
So 1 over tau is increasing, and yeah. So that now, sorry, now it's
everything I read is literally is one slide proof. But if it like this.
Yeah.
And there he has some estimating sequence and
So the estimating
now you
sequence.
have just replaced that by saying that okay, I reduce the distance by half and then I change by the
So the estimating sequence is still there. That's the
Yeah.
thing. That looks like the estimating sequence. But the thing is, there it's like with the estimating sequence has the quadratic, and the quadratic is like it's less than 1 minus lambda times the function plus the initial quadrant. Here you say no, I just combine the two values there. So it's like take solving to the top and taking the that's already good.
Yeah, exactly. Yeah. Does he? I guess another Batra would also work for other norms, right? Would it not? Not sure.
Other norm.
I mean, because this works for any norm actually. Here we're not using it anyway. because you use Bregman divergence in the mirror, right? So even if it was other norm and you have like an edge, this goes through.
Well, in the.
But with the mirror version.
What does it mean, right? So because in game he wants to say something that fx minus like so there's no norm, it's about the number. So it's like you have to look at how far the value is from the minimum value. Like what is fx k minus fx star?
Yeah, no. What I mean is that if your function is smooth in some other norm.
Or else smooth in some other norm.
I guess it should still work. I don't see any why not.
Instead of because like the Taylor approximation sort of makes sense. Correct.
Yeah.
But we got some Google thing. They'll have to change topic. Not just be for become strange.
Wow.
It's something other.
Okay, anyways, so I want to like just yeah, one more fun. A little final text close off this part. I just want to like make some other comments about some other results. So there's another item called coordinate descent. I want to make comments about that. Because this kind of idea is useful there also. So just recall, okay, so really, just recall what coordinate descent is. So what's the idea? So the idea is that instead of getting not a full gradient, you sample the coordinate and update only that.
We have the direction derivative.
Yeah. Yeah, and the idea is that because sampling in expectation you'll end up updating the full gradient. Yeah. Okay. And now usually if the function is Li smooth for coordinate drive, then typically you okay at least yeah, earlier the idea was to sample coordinate I with probability proportional to the line. Okay, so this is for regular as well. I suppose it's sample probability proportional to the line. And okay, but it turns out that okay, so using the analysis similar to what we just showed, turns out it converts faster if you sample proportional to the probability proportional to square root of. Okay. Okay, so yeah, so I want to kind of sketch intuition for why this should be done. So what's the intuition here? So let's look at so yeah, let's take nice equations. So f of x k plus 1, f of k plus 1, at least 1 over 2l. Right? This is what we know about gradient descent. And for gradient descent, we know that eta dk minus u. This is what we just derived. So okay, so another point is okay, so what if a select coordinate? So the select coordinate I, then roughly speaking, this is like the partial derivative coordinate I, or gradient I, f of x square, something like this, right? And what about here? So okay, so if I want this side to remain the same in exploitation, then this thing here should be something like 1 over pi gradient I. Okay. So okay. So yeah, so and now if you do that, then this thing here becomes gradient I square to pi square, right? And here you have to like okay, so yeah, so okay. So now if you compare these sets, you compare this with this. Then yeah, then if you want these things to cancel, so remember in our analysis, right? We go here. Yeah, okay. So so how had we balanced the two things? So we had balanced uh, this difference.
Okay, get this one to cancel. This one and this one.
Yeah, exactly. So we wanted this to cancel. So we are trying to equate this coefficient to this coefficient. And how had we gotten these two coefficients? So yeah, so this was essentially your coupling and your JD step, right? Essentially. So yeah, so you want these things to cancel, and now if you want things to cancel here, essentially you do this whole thing and you want things to cancel, then yeah, yeah. So essentially you will want these things to cancel out, and yeah, and therefore PI should be roughly root away. Okay, I guess I'm not sure how good it is looking like this. But okay, I guess the point is that by using the kind of analysis that we just did, you can obtain a better convergence rate for coordinate descent. So yeah, essentially you do the same kind of coupling of the two kinds of objects, and you choose this sampling probability, this sort of LI, and then you can get acceleration for coordinate descent also. Okay, I guess like a lot of papers on using coupled variations of data descent and data descent. So I guess I'll try to show. Yeah, bunch of stuff. Okay, I guess yeah, that should be so. The next time we'll do two topics. So the first end of optimization. So then the next time we'll go to our Greg Yang tensor program. And I will share some the papers for this. And by the way, these comments, there are some other works which we did go to. So you can also get acceleration for other kinds of stuff. So using these ideas, there's another paper which tries to get acceleration for converging to saddle points. And again, using this kind of coupling tricks, you can do that. So saddle points even for like non-convex functions.
Some point, I mean, oh, I guess you wanted the saddle points, then you are thinking of this convex in one way, or concave in another.
No, like it's even easier than that. So, but saddle point, I mean that. So remember, get this result that you can escape saddle points, but in this random moves. But that depending on some properties of the function. So you have to assume that your function is Hessian Lipschitz, and it has this no. It has this
Gap.
gap between the eigenvalues. But more generally, if you want to obtain a saddle point, okay, so I mean, if you don't have those properties, then the best you can ask for is to reach a saddle point. Then you can't really escape saddle point, and we kind of work on how fast you can reach saddle points. So yeah, and then one asks if one can do that in an accelerated way, and yeah, and by using these interpretations, you can do those things.
No, you said that even for non-convex function, you can reach by a saddle point. How do you reach saddle point in a convex function?
If it's convex, then
if it's convex, then there won't be saddle.
then they want saddle points. So then you don't care. Another line of work is this of solving LPs. In particular, this line of work on robust LPs. So you have like a bunch of constraints, and you want to maybe minimize the you want to keep the L1 error small on the constraints. So specifically, if you have a problem like this, actually maybe this put it in homework maybe.
So you don't have to satisfy the constraint exactly.
Yeah. So let's say you have something like this. It's linear things, and you want C transpose xi minus BL. But let's say you have L1 now here. Yeah, so that's what it should satisfy the max as possible, but you always measure it in L1 now. And here again, it turns out that using a different norm while doing optimization is better. So I think it is a pretty. Another is boosting. I think, yeah, I guess bunch of different things. Anyway, I guess lots of different applications. Anyways, yeah, thanks.